Okay, here we are. Quantitative chemistry, the ideal gas equation. Open your data booklet and then check out these values that you'll find in there. You'll find the ideal gas equation itself, PV equals nRT. You'll find the gas constant, 8.31 joules per Kelvin per mole, and that is not the molar volume that we're interested in. This is the value of 1 atmosphere pressure measured in pascals, 1.01 times 10 to the power of 5 pascals. You'll find that there as well. All very useful. The ideal gas equation includes pressure. Let's use pascals when we do that. We use volume of the gas. Let's make sure we use cubic meters. N is the number of moles. And temperature, very important, we need to use the Kelvin scale for temperature. And R is our gas constant. And by using and rearranging that formula, we'll be able to solve problems to do with ideal gases. And if we use the units I've mentioned, pascals, cubic meters, moles, Kelvin, and this gas constant, we can't go wrong. There are other values for the gas constant with different units, but if we use this one and the units here, you can't go wrong. Let's do an example. From the booklet you've been given, question 2 says that we want to find the volume of a gas. We're given 0.400 moles of a gas, and we know that at that gas is going to be at a temperature of 100 degrees C, and there's a pressure of 1000 kilopascals. We're trying to find the volume. Okay, well, we know that PV is equal to nRT. First of all, let's make what we're trying to find, volume, the subject of our formula. So V will become nRT over the pressure. The number of moles we have is 0.400. Multiplying by our gas constant from the data booklet is 8.31. Temperature, we have to convert to Kelvin. That's 100 degrees C plus 273. I'll show my working. I'm going to divide by pressure. And pressure says here we want it as it's given as 1000 kilopascals. Well, that's 1000 kilo is times 10 to the power of 3. And if we work that out on our calculators, I hope we'll find that as I get 0.0124 cubic meters. I've given 3 significant figures there. Does that seem reasonable? Well, it depends on how precise we're assuming they are. If we assume that all those digits are significant, I feel we can give 3 sig figs there. So any time we're going to work out anything to do with the ideal gas equation, we're going to make sure that we arrange this first into a suitable form. Another very useful use of the ideal gas equation is when we're trying to find relative molecular masses. If I look at number 6 from the sheet you've been given, it tells me that I've got a temperature of 273 and a pressure of 101,000 pascals, and I've got 6.319 grams in a volume of 2.00 cubic decimeters. It wants to know the relative molecular mass, or the relative molecular mass. Well, the ideal gas equation can be written as PV equals nRT. We know already that the number of moles is equal to the mass over the relative molecular mass. So our equation can be written as PV equals M over MR RT. And so if we're trying to find the relative molecular mass, we can rearrange our formula to give us relative molecular mass being equal to the mass multiplied by the gas constant times temperature divided by the pressure volume. So that gives me the mass is 6.319 grams. The gas constant is 8.31. The temperature is given in Kelvin as 273, so we don't convert. The pressure is given as 101,000 pascals, and we've given decimeters cubed as our volume. Well, to convert that to meters cubed, we will divide by 1,000 or multiply by 10 to the power of negative 3. And so then we'll have, if you do that with me, I get a value of 71.0 to 36 figs. Ask yourself a question: does that seem reasonable for a value for a molecular mass? Indeed it does. Of course, if you're getting a value in the thousands or a value below 1, you need to start asking yourself questions. Alarm bells should start ringing. That seems reasonable. Okay, thanks. That's enough for now.